Unit 3 is about volumes of solids of revolution. So what we will do is take functions and find the area under them with a picture and then revolve them around the x-axis or y-axis or different axes. And that area becomes a volume in 3D once you revolve it or rotate it. Did you ever wonder how volume formulas were determined? Well, let's think about a cylinder and maybe think about a log that's round and tall. So how can we find its volume? Well, we can slice it infinitely many times, add up all those areas of each slices as we did with the Riemann sums. Remember, we took the sum of the areas of a finite number of slices, then drag that out to infinity using a limit. When we slice the cylinder, again, think of a log, we get a circle. The area of a circle is pi r squared. The cylinder is sliced from 0 to its height h. So as you slice the log, you're going to get all these circles and you're going to add up the areas, which will give us the volume of the cylinder, which is pi r squared, which is the area of the circle, times h, the height of the cylinder. We will think of a slice in the future as a rectangle. So we will take a rectangle, the representative of the area under a function, going around a specified axis. So think of it like this. Here's the x-axis, and here's the rectangle, and when you rotate this pen, or think of it as a rectangle around, you get a disc. Think of a nickel or a dime. It's a thin disc. So in that case, we'll use pi r squared for the area of that disc. If you go around and it's not touching the axis, like this, you will get what's called a washer. So think of when you use nuts and bolts, think of that flat metal piece, because it's going to be flat, as a washer because it has a hole in it right here as it goes around, because it doesn't touch the axis, it has a hole. So here's a rectangle going around, and that's going to be a washer. So you're going to take the large circle and you're going to subtract it from the small circle. Then if you take a rectangle and go around this way, you're going to get a shell, like a paper towel holder, and it's going to be hollow. And so in that case, it's a shell. We call that a shell. So it's long and hollow, whereas discs and washers are thin. The last part of the unit involves two cases, and they allow us to integrate with infinity as our bounds or a discontinuity. The idea is to integrate with finite bounds and drag those bounds out to infinity using a limit, or to get infinitely close to the discontinuity. The most interesting fact is the area under the curve f of x equals 1 over x. Because if you integrate and get the area, it's an infinite, whereas if you take 1 over x, which looks like this, around the x-axis, you're going to get a volume, and that volume is finite. So the area is infinite where the volume is finite, and that is called Gabriel's horn, or Gabriel's trumpet. We will also discuss convergence and divergence for the first time, and we will use improper integration and convergence and divergence in upcoming sections.